I'm Tim. This PCB Sync.
In this video, we'll go through the Rogers RO4350B datasheet item by item. We'll focus on what DK, DF, TG, TD, CTE, thermal conductivity, and water absorption mean, and how these parameters affect high-frequency PCB design. All the values in this episode are based on the typical values and test conditions from the official Rogers datasheet. So the first item we'll look at is the dielectric constant, dK. The standard thickness RO4350B has a dielectric constant of 3.48 plus or minus 0.05. The test conditions are 10 GHz at 23 degrees Celsius using the clamped stripe line method. For transmission line dimensions, electrical length, and resistance simulation, Rogers also provides a design dielectric constant of 3.66, tested at frequencies from 8 to 40 GHz. The differential phase length method is used. The manufacturer DK is mainly used for material specifications and production DK process control, while the design DK is more suitable for circuit design. So when designing for impedance and phase, you can't just look at 3.48 and apply it directly to all models. In addition, there's an exception. For RO4350B with a thickness of 4 mil, the manufacturer DK is 3.33 plus or minus 0.05. Before designing, you must confirm the specific thickness. The second point is the dissipation factor, DF. At 10 GHz and 23 degrees Celsius, the typical DF value is 0.0037. At 2.5 GHz and 23 degrees Celsius, the typical value is 0.0031. DF reflects dielectric loss. Generally speaking, the lower the DF, the less signal loss there is as it propagates through the dielectric. But the final insertion loss is not determined by DF alone. It is also affected by copper foil roughness, copper thickness, trace width, surface treatment, connectors, and manufacturing tolerances. So, in high-frequency design, you can't just compare a single DF value. You also need to consider the complete stack-up and the actual structure. Next, let's look at a few parameters related to heat resistance and reliability. RO40 and 4350B have a glass transition temperature greater than 280 degrees Celsius, and their typical decomposition temperature is 390 degrees Celsius. Both TD and TG reflect the thermal performance of the material, but neither can fully represent the overall reliability of a PCB during reflow soldering thermal cycles or long-term operation. We also need to look at the coefficient of thermal expansion, or CTE. The CTE of the Rogers RO435B material in the X, Y, and Z directions is 10, 12, and 32 parts per million for every degree Celsius, respectively. The CTE in the Z-axis is especially important because when the board expands along its thickness, it creates significant mechanical stress on the copper in the plated through-hole connections. For multi-layer boards, thick boards, and high aspect ratio vias, the Z-axis CTE will directly affect reliability under temperature cycling. The standard characteristic thermal conductivity of RO4350B is 0.69 watts per meter Kelvin when it's measured at a temperature of 80 degrees Celsius. Thermal conductivity indicates the ability of heat to transfer through the board material. The higher the value, the better it usually is for dissipating heat from localized areas to the surroundings. However, the actual temperature rise of the PCB is also related to factors such as copper layer area, copper thickness, thermovias, device packaging, metal base plate, and external cooling conditions. The typical water absorption rate of RO4350B is 0.06%. Water at 50 degrees Celsius, soaking time of 48 hours, and sample thickness of 0.06 inches. A lower water absorption rate helps reduce the impact of humid environments on the material's electrical properties and dimensional stability, but this doesn't mean that the dielectric constant, dK, remains completely unchanged under any humidity. Another very important feature of RO4350B is that it meets the UL94V0 flammability rating. For communication equipment, industrial equipment, and other products that require flame retardant certification, this directly affects material selection. It is also compatible with lead-free processing. The typical copper foil peel strength is 0.88 newtons per millimeter, which is equivalent to 5 pounds per inch. Although these parameters aren't discussed as often as DK or DF, they do affect manufacturing, assembly, and final product certification. So, to sum up, DK affects impedance, propagation speed, and electrical length. The dissipation factor reflects the dielectric loss, but it's not the only source of overall insertion loss. Similarly, the glass transition temperature reflects the material's heat resistance. CTE, especially Z-axis CTE, is closely related to via and temperature cycling reliability. Thermal conductivity affects the board's ability to transfer heat. Water absorption is used to determine the material's stability in humid environments. And UL94V0 is about whether the product meets certification requirements. Once you understand these parameters, you won't just choose materials based on DK and DF alone. Instead, you'll make a comprehensive judgment from the perspectives of electrical performance, thermal reliability, certification, and manufacturing requirements. If you're designing a high-frequency printed circuit board using RO4350B, PCB Cinia can assist with material recommendations, stack-up evaluation, impedance calculation, DFM review, prototyping, and mass production. Scan the QR code in the image and upload your Gerber files to start your inquiry. If you found this episode helpful,